welcome. So, today and for the next couple of days, we are going to be dealing with rates of change, okay? Which is the first unit of calculus. So that's why we do it. Historically, we've always done it as the last unit of pre-calculus, which then is your first unit of calculus. Yeah?
So we're going to do the test over again for this next year?
Like, what do you mean?
Like, so are we still going to do this unit next year? The same one?
You'll have a refresher of it, yes.
Okay.
Yeah. We will have a test on this unit during finals week. Now, for those of you that were in homeroom this morning, you saw that the pre-calculus final is given at 2 different times. One of them is on day 2, period 3, which is the Friday. The other one is on day 3, period 1, which is on the Monday. Okay? You have to sign up, and we'll put that sign-up sheet out later on for which one that you get to sign up for. All right, so let's get into rates of change. And then we'll talk about this for a while, and then I covered a Hill class this morning, and we were done with plenty of time left in class for you guys to work on some worksheets. Okay? So, let f of t equal 3t squared, and let's let that represent the distance in meters an object is from its starting point in t seconds. Okay? So f of t equals 3t squared. That's going to represent how far away the object is from the starting point after a certain amount of t seconds. Question number 1 that I'm asking is, how far has the object traveled in 4 seconds? How will we figure out how far it traveled in 4 seconds? Well, yeah. Plug in 4 for t. So we're going to find f of 4. So in the first 4 seconds, it traveled 48 meters. Agree? Okay. How far did the object travel in 8 seconds? What do we do with that one? Plug in 8 for t. What do we got?
No.
192?
Oh, yeah. Okay.
Big question now. How far did the object travel from the end of the 4th second to the end of the 8th second? Okay, yeah, exactly. You subtract the 2. So this would be f of 8 minus f of 4, which would be 192 minus 48. So it traveled 144 meters. Yes? What is the object's average velocity average rate of change is what we're going to call that, from the end of the 4th through the end of the 8th seconds. Well, this here is our new concept then today. And our new concept today is AROC. AROC is average rate of change. I know, stepped way outside the thinking on coming up with that anagram. Okay? How we solve AROC is we do delta y over delta x, the change in y over change in x. If you think about it, rates of change you've already learned back in Algebra 1 when you were talking about slope. Change in y's over change in x's. Okay? In this particular case, it's the change in distance over the change in time. Okay? So if I'm talking 4th through 8th second, that's going to be f of 8 minus f of 4, which is the change in my distance, how far the object traveled in the first, or in those 4 seconds, over 8 minus 4. Well, we've already done most of this math. We said that that was 144 meters. We said that that was 4 seconds. So 144 divided by 4 is 36 meters per second. Okay. And this is the AROC of the object over the interval 4 seconds to 8 seconds. Okay. Delta S over delta T, we just called it delta distance over delta T. Okay. That's also called the difference quotient. Okay. And the dq gives us the average velocity of an object over a period of time. Unlock this. There it goes. Now it fits in there. Average velocity, the AROC of an object over a period of time, A to B. Okay. In calculus, we can use a bunch of different things, okay, and we can make a dq out of it. Okay. Oil spilling, amount of sand piling up in the shape of a cone. Okay. 2 cars traveling along. Okay. It's a big race weekend if you're a big race fan. You have the Indy 500 every Memorial Day weekend and the big NASCAR 600-mile race. And so you can see how 2 cars are traveling next to one another. You know, are they getting closer? Are they getting farther away, etc. We can find that, okay, using this kind of thing. All right. Rates of change, remember, distance divided by time. That's our rate. Okay. All right. So, if f of t is 3t squared, meters an object is from a starting point, you find me now the AROC over that interval. So the AROC on the interval 3 to 6 seconds is going to be f of 6 minus f of 3 divided by 6 minus 3. F of 6 is going to be 3 times 6 squared, which is 36 times 3. What's that, 108?
Yep.
F of 3 is going to be 3 times 3 squared, which is 27. What's that, 81 over 3? So my A rock is 27 meters per second. Yes? Now, we found the A rock 4 to 8, right? We found the A rock 3 to 6. The A rock from 4 seconds to 8 seconds was 36 meters per second. The A rock from 3 to 6 was 27. What can you tell me about the object? Give me another chance. Three to 6, it was 27. 4 to 8, it was 36. So if it was slowing down,
average, yeah, never mind. Other way. So it's average between those
it's
two
speeding
scales.
up.
Yeah.
Yeah, it's speeding up. It's getting faster. Okay, because the number was going up. Yep. If the numbers would be the same, it would be staying at the same speed over both of those intervals, or at the same average speed. Okay. This one's speeding up, though. Okay. All right. So, instantaneous velocity now. Again, let's step outside the box, and on the anagram here, we're going to go with IROC, instantaneous rate of change, not average rate of change. Okay? That's still going to be change in distance over change in time, but now we want our time to be 0. We want that change in time to be 0 seconds. Or something really, 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 really infinitely small, because we truly can't divide by 0. Okay? So what we can do is we're going to change up our function here a little bit. We're going to go d of t is now just t squared. We're going to have that represent the distance in meters an object is from its starting point in t seconds. Okay? So we want to find the instantaneous velocity at 3 seconds. So I could say something along the lines of, let me find the A rock from 3 to 3.5. Right? Because that half of a second gap is nice. Okay? Oops, excuse me. Change it up to D. So I'd set it up like that, right? 3.5 squared is what? 12.25?
Yeah.
I think it's 12.25. 3 squared is? 9.
Yep.
12.25 minus 9 is 3.25, right? .5 minus 3 is 0.5. Yes? So that gives me an average rate of change in a rock here of 6.5 meters per second. Agree? But in terms of instantaneous, 0.5 is a lifetime. 0.5 of a second is a lifetime when we're talking instantaneous. So let's shorten that up even more. What do we want to go to now? 3.1. Okay. Find me the A rock now for that interval of time on D. What do we got? 6.1. Because we get 9.061 minus 9 all over 3.1 minus 3. So we get 0.61 divided by 0.1, which is 6.1. Yep. Okay. But still, I mean, when we're thinking about instantaneous, yes, 0.1, a tenth of a second is small, but in instantaneous world, it's still pretty big. Okay? So let's go even smaller. Find me the A rock for that one. .01 squared is 9.0601 minus 9 is 0.0601 divided by 0.00 or 0.01 is 6.01. So it looks like the IROC is what? 6? Okay. It looks like if we would keep going, this number is getting smaller and smaller, closer and closer to 6. So I would venture to say that the IROC at t equals 3, so the instantaneous rate of change at t equals 3, at 3 seconds, is 6 meters per second. Okay. Now, mathematically, we can use something called limits to prove that. Okay? So, same function, s of t equals t squared. Okay? But now using limits, I'm going to find my AROC of 3 to t. Okay, so my interval is from 3 to t, and what I want to do is I want to send t to 3 seconds. So that becomes instantaneous. Sorry, I lost my train of thought there. Okay. And what I do here is I say that this is the limit as t goes to 3 of this, of the AROC of this. Well, that's going to be S of t minus S of 3 all over t minus 3. Right? Now I can't straight up plug in 3 for S, or for t. I can't do that right now, because if I did that, I'd have S of 3 minus S of 3. Well, what's anything subtracting itself? It's 0. And then I'd have 3 minus 3. Well, that's 0 again, and so I get 0 divided by 0. Okay? And we can't do that. Okay? So that's, we can't just straight up substitute t equals 3 right off the start. But we can use math, and we can go through our limits, and we can figure it out. So we're going to keep the limit notation on and active as long as we can. Okay? S of t is t squared. Right? S of t is t squared. S of 3 is what? 9. T minus 3 is t minus 3. Mathematically, is there anything that we can do here with that? Fantastic. So this is going to become the limit as t approaches 3 of t minus 3 times t plus 3 all over t minus 3. Mathematically, the t minus 3's now cancel each other out, right? So that leaves me with the limit as t approaches 3 of t plus 3. And now I don't have a denominator that I have to worry about. So now I can substitute 3 for t. So then this is now going to become, I get rid of my, when I substitute in that value, I get rid of the limit notation. So now this is 3 plus 3, which gives me an IROC I don't like how that's written. That's a bad at. Which gives us our 6 meters per second. Okay? What I'd like you to do now is in number 1, I would like you to find me the AROC, the average rate of change over that interval. And in number 2, I would like you to find me the IROC at t equals 1. Alright, so the AROC here on the interval 1 to 4 is going to be f of 4 minus f of 1 all over 4 minus 1. If I plug 4 into my function, I get 32, right? F of 4 minus 3 is 29, yes. If I plug in 1 into my function, I get negative 1. So that's 30 over 3, which is an average of 10 meters per second. Yes? Okay. Love it. IROC of S at t equals 1 so that's going to be f of t, s of t. Probably should go up and change that on the other ones too right away. Since we were talking with S here. Right? But that, I forgot. I'm going to move this over now. We want the limit of that as t goes to 1. So s of t is 2t squared minus 3. S of 1, we said from before, was negative 1. So that's going to be 2t squared minus 2 all over t minus 1. Right? A little sideboard action. 2t squared minus 2 is 2 times t squared minus 1 is 2 times t minus 1, t plus 1. Right? So then this becomes then those go there. Right? Now I don't have a denominator to worry about. Now I can substitute in 1 plus 1 is 2. 2 times 2 is 4. So the IROC at 1 second after the object is released is 4. We'll keep it with meters per second since that's kind of what we've been doing today. Okay? Questions?
Is that how it's supposed to notate it? Is IROC at 1 second?
it's an answer blank, I'm okay with it. Okay. So I handed out 2 worksheets for you today. Actually, it's 3 worksheets because A and B are on the same one. Okay. If you want to do A, you can do A, but you can skip A if you want to skip A also. Okay. And start with B and C then for today. Okay.